Okay, thank you very much for the introduction, and I also would like to thank the organizers of this very beautiful conference for giving me the opportunity to speak and to present our work. So immediately the disclaimer, this is going to be a theory talk, so no experimental results. So as we all know, so in the past decades it was demonstrated that lights or photons can be used not only as a spectroscopic way to probe properties of various physical systems, but also as a way to change their properties. And the specific experimental examples include the possibility of enhancing conductivity in organic semiconductors, control of chemical reactions, modification of superconducting transition temperatures, and also the modification of the integer quantum Hall effect that is seen yesterday in the beautiful talk by Jérôme Feist. At the same time, in the condensed matter community in the past 20, 30 years, there has been a lot of research activity in the field of topological materials, and more specifically on topological insulators and topological superconductors. And the motivation comes from one hand from theoreticians, because these materials have very specific properties, they obey non-abelian statistics, they are very stable and so on, but also from potential applications in the field of quantum technologies and quantum computing more specifically. So a typical example of topological material is one-dimensional topological insulator, which is described by a prototype Schiffer-Heeger model. So this model was introduced in 1979 to describe polyacetylene atoms, and since then it became a textbook example on how to explain students what is bulk edge correspondence, what is a winding number, what is a Wilson loop, how to diagonalize Hamiltonian in real space, in momentum space, and so on. So very briefly, this model describes a one-dimensional chain which consists of two sublattices A and B. And one can have two types of hopping between these two sublattices. So there can be this hopping small v, which is a hopping within the same unit cell but between two different sublattices. Or you can have a hopping W, which is between two different sublattices and two neighboring unit cells. So in this talk, I will always talk about the finite size systems when we have, let's say, 100 unit cells or 100 lattice sites in a setup. So if we take this Hamiltonian of finite length and we diagonalize it, since we don't have any electron-electron interaction, we can do it in a single particle picture, we obtain the energy spectrum that looks like this. So from this energy spectrum, we can learn that we have two L energy levels or 200 single particle energy levels, and when these two hoppings are equal, sort of these levels come together and we can say that the bulk gap closes. But then if one of these hoppings is larger than the other one, we can see that there are two states appearing at zero energy, and these states will be topological edge states, but in the opposite regime, when this hopping between neighboring unit cells is smaller than the hopping within the same unit cells, you don't have any zero energy states, and we can say that the system is in a trivial phase. So this talk will be more focused about one-dimensional topological superconductors, and I will introduce the models in more detail a little bit further into the talk, but just what are the specific properties, why are so interesting from fundamental point of view. This is a superconductor, so in this case we have this nice superconducting gap in this setup, and if you want to get these Majorana bound states, which is a special properties of these topological superconductors, they will emerge exactly at zero energy, and the state will be doubly degenerate. And what is more interesting is these two Majorana bound states in one-dimensional systems, they will emerge at the opposite ends, making them a very highly non-local objects. So in this talk, I'm going to combine these two different theories of light-matter interaction and topological materials, and to see what we can learn in this case. So in the past few years, there have been a number of theoretical works that consider this SSH model couples to photons or some other models for topological superconductors. And just to show you a few examples, mostly from the people present in this room. So there was a study by Martin Claassen et al. About the SSH model coupled to photons. Then there was this very nice work by Marcello Andolino. He gave a previous talk where they considered the ladder model for superconductors coupled to photons. And there is also this very recent work from Cristiano Ciuti's group where they considered SSH model coupled to photons and how this coupling to photons modifies transport in the SSH setup. But since this is a theory talk and there are many people who are theoreticians in this room, the very important question is how to couple our electronic system, or more specifically our topological insulator, topological superconductor to photons. So when we work in the continuum, when we work with realistic systems, we can say that, okay, we fix the gauge of our problem. For example, let's say we say that we describe our photons via the photonic vector potential A, and then we can just do a minimal coupling substitution to couple our solid to photons. Or we can say that, okay, we want to describe photons using the electric field E, and then the coupling is described as a coupling between the electric field and the dipole moment of the matter times, plus this dipole moment squared. However, we cannot deal with this whole complexity of solid, and often we already have the models, like SSH models that we want to couple to photons. So we don't start with this big continuum model and then project it onto some band. So what do we do in this case? And in the past 5 years, there have been a number of works that address this issue. So one of them also coming from Dennis Golitz and Martin Eckstein, where they propose this multi-center PZW transformation to couple solid to photons. Another option is to start from this dipolar gauge or length gauge, but in that case there is an issue of the translational invariance, which was addressed in this recent work from Daniel Lo's group in Basel. But since, especially maybe for experimentally, they're more used to the pi substitution, which in a case when you have only a single orbital in a system, is just addressing of the hopping amplitude with the phase A that depends on our photonic operators NA and dagger. So in our work that we did with Marcos Kira a few years ago, we demonstrated that we can if we start with a tight binding model and we couple it to photons, we can do it through a unitary transformation that depends on these photonic operators A and A dagger, but also on the electronic operators, which were projected on the same subset of Wannier orbitals as our tight binding model. But the important point here is that if you use this unitary transformation approach, we exactly recover the pi substitution in the case of a single orbital model. So in the rest of this talk, I will focus on very simple systems with a single orbital. So I will just use a pi substitution to describe the coupling between my electronic system and photons. So just an idea how it works. For example, if you take an example of the SSH model, which is slightly modified. So instead of saying that the distance between different sublattices is the same, we just add some shift B0, and we couple it to our single mode cavity with cavity frequency omega c and photonic equation and annihilation operators A and A dagger. We introduce this coupling via the pi substitution, meaning that our hoppings within the same unit cell and between two neighboring unit cells gets addressed by a phase. So this phase depends, it's highly non-local because it depends on all the photonic operators A and A dagger. It depends on the strength of the light matter coupling G, and it is scaled with the number of the unit cells in the system, and of course on our shift between two different sublattices. So the first question as theoreticians we have, so how do we solve this Hamiltonian? Back in 2022, we decided to do a mean field decoupling between electronic and photonic degrees of freedom, neglecting all the fluctuations between the two systems. And what we found that in case if we don't have any coupling to photons, we get this black energy spectrum for the SSA chain in the lowest photonic band. But then once we add this very large coupling to photons, it turns out that we can sort of shift this electronic eigenvalues to the left and to the right, depending on our choice of the distance between two different sublattices. And the conclusion is that we made at the time is that by coupling our electronic system of finite lengths to a single mode cavity, we can change the topological properties or the parameter regime when we obtain the formation of these zero energy states in a setup. So another topic, yes, please.
So is this mean field decoupling actually valid if you go to large interaction strengths?
You mean light matter interaction G?
Yeah, because you write as a tensor product of electron and photons.
Yes.
So, but there could be actually entanglement between these two subsystems when you have large linear interaction.
Thank you. So in principle, the mean field is valid in the thermodynamic limit, but in the thermodynamic limit, the single mode cavity has no effect on our electronic system because of this scaling square root of L. Of course, it's been demonstrated that mean field misses fluctuations, but just for the shift of the energy spectrum, it's more or less fine, I guess, to use the mean field. But of course, now there are more developed methods, for example, in the work by Martin class, and they used the DMRG with photons approach, or one can use exact diagonalization. And some properties are missed.
I guess another question is that, like, how do we know the sublattice symmetry is not broken when you have such a large light matter coupling, right? So the SPT might be gone, actually.
Yeah, so that's an excellent question. So actually, that's the topic of this paper from the group of Gloria Platero and Alvaro Gomez-Leon. So they studied the SSH model coupled to photons, and they solved it in a single particle electron system. And they demonstrated that the chiral symmetry, sublattice symmetry, which is responsible for formation of the zero energy states, is broken. Yes. So now more into the direction of the topic of this talk about Majorana bound states in topological superconductors. So very brief introduction. So the concept of Majorana fermions was introduced by Ettore Majorana in 1937 as a real solution to the Dirac equation, such that one can say that this Majorana fermion is a very special particle that is its own antiparticle. And then this concept was reintroduced in the condensed matter physics. However, in this case, one should look not for a real particle, but more of a quasi-particle, which should be unequal superpositions of electrons and holes, such as a Bogolu-Born, in order to ensure this property of particle being its own antiparticle. So on a theoretical level, so usually in condensed matter physics, we work with fermionic creation and annihilation operator C, which are by usual anti-commutation relations. But then one can just do some exercise and introduce the Majorana operators, which is just a linear combinations of creation and annihilation fermionic operators. And then it turns out that these new gamma operators have this very special property of gamma being equal to gamma dagger. So you can also see this gamma as a Bogolu-Born in the theory of superconductivity. So the prototype system of these p-wave superconductors was introduced by Kitaev in 2001, and it's called the Kitaev chain model. So one starts with a very simple non-interaction Hamiltonian with no spin, which just describes one-dimensional chain of, let's say, n sides, and one can have on-site energy or on-site chemical potential mu, hopping between two neighboring sides T, and the special type of superconducting pairing, which is called a p-wave pairing, that couples electrons on two neighboring sides. And then one can solve this problem analytically in two different regimes after rewriting these fermionic operators in terms of Majorana operators gamma. So in the first case, we assume that there is no superconducting pairing, there is no hopping, there is only on-site energy, and we arrive at this Hamiltonian written in the Majorana basis. And it turns out that all the sort of Majorana operators are coupled, and there is nothing interesting happening here, so we can claim that the system is in a trivial phase. Alternatively, one can look at the opposite regime when there is no on-site energy, but our hopping is equal to the superconducting pairing. And in this case, the Hamiltonian is greatly reduced, and it turns out that the Majorana operators on the very first and very last side are uncoupled, and they correspond to zero energy modes of our setup, something that we should be looking for. And then if we look at the single particle energy spectrum of the system, we can see that similarly to the SSA chain, when the hopping is equal to chemical potential divided by a factor of 2, sort of this bulk states, they go to zero, they close, and then for small values of mu, one can see the emergence of the zero energy states, and in an opposite regime, you just have a superconducting gap and nothing in between. And if we take, for example, state here, and we look at the probability density of the state as a function of the lattice side of our system, we can see that this zero energy state has a probability density red one, meaning that these two zero energy states, they live at the opposite ends of our one-dimensional chain. And if we pick up one of these bulk levels, we plot the probability density, and it's a standard sort of particle in a box solution for the bulk states. So then comes the experiment. So the proposal to realize this pure superconductivity in real life, the one that received the most experimental attention comes from Luchin and Orek, and it was put forth in 2010. And it's based on effectively engineering pure superconductivity with three ingredients, by starting with a semiconducting nanowire with Rashba type of spin-orbit interaction, proximatizing it with a superconductor to generate effective superconductivity in the system, and then applying magnetic field in the setup. And then the experimental signatures that were afterwards observed in many experiments, they consist in the observation of the peak at zero bias in the differential conductance, because these Majorana bound states have zero energy. However, as many of you probably know, this type of experiment sparked a lot of discussion, in particularly whether what they see is really the Majorana bound states or something else. So the first experiments were performed in 2012, and here is the measurement of the differential conductance as a function of the gate voltage for different values of the magnetic field. And when magnetic field becomes larger than some critical value, one can see the emergence of zero bias peak, which was interpreted as a signature of the Majorana bound states. And later on, Microsoft Quantum has greatly improved the quality of the samples of the setup, and they demonstrated this is a density plot of the differential conductance as a function of the applied magnetic field, and they showed that at some critical value, sort of these two levels go to zero and stick to zero over a wide range of the parameters. However, a number of theoretical works discussed whether the zero bias peak can emerge due to the presence of the smooth potential or zero energy Andreev bound states in a setup. And this obviously sparked a lot of discussion both in theoretical and in experimental communities. That's why in the past few years, a different approach is being considered in the community, especially by experimentalists, on how to realize these Majorana bound states. And it's called bottom-up approach, that instead of starting with these long nanowires of a few micrometers, or that consist also with these hybrid semiconductor, superconducting heterostructures, maybe one should start with a simple system which consists of two quantum dots, which are coupled through a superconductor, and the superconductor in between, it ensures both the tunneling between two quantum dots and also the cross-Andreev pairing between the two. And it turns out that from theory point of view, such a system, which was proposed in 2012, but did not receive much attention at the time, can be described just by a two-side Kitaev chain model with on-site energy mu, hopping T between two neighboring sites, and superconducting pairing delta that couples sort of two sides or two quantum dots. But then, since this is a quantum dot, we should also add a column interaction term in a setup. And then it was introduced that in such a setup, not like Janine, but Pullman's Majoranas can emerge. So how can we see that? So we start by this two-side Kitaev chain model, and we can easily solve it in a many-body picture. So we can introduce our Hilbert space, and we can have 4 possible states in a setup. And then it turns out that by diagonalizing this Hamiltonian in 2 different many-body sectors, we can calculate the ground state energy in both sectors. And then, in order to have this double degeneracy of the Majorana bound states, we impose a condition that these ground state energies are equal, such that we can have this Pullman's Majoranas when we don't have any electron-electron interaction, and when the hopping term is equal to the pairing term. Alternatively, the emergence, yes, John.
Okay, maybe I'm a little confused, but the Majoranas, at least as you showed before, the Majorana states were pinned at zero energy by particle-hole symmetry, and now that is not the case.
Okay, so here, so there are two ways to look at it. On one hand, we can look at it in single particle picture, then they pinned at zero energy. But if you look at it in the many body basis, then one should look for a ground state degeneracy between even and odd parity sectors.
Mm-hmm. Okay, because you're saying it's a two-site system, so there's some hybridization, so they would never be at zero anyways, and also there's interactions, and so we should just look for degeneracy.
In principle, yes, but if you want to get like the Spurman's Majoranas at zero energy, so what I'm going to show in the next slide, we can rewrite this Hamiltonian in the Majorana basis, and we can apply exactly the same condition as before for the long chain to want to have these two border Majorana operators drop out of the Hamiltonian. And if we were to come back to a single particle picture, we will find that the single particle eigenvalues, they are at zero energy.
Thanks.
Yes, please, there is another question.
Maybe you'll talk about this later. Like, is there anything special about quantum dots? Like, naive I think you can just build this Hamiltonian for, like, different systems since it's the
okay, so about the quantum, maybe wait one more slide, and I will answer your question, okay? Yeah, so another way to see that we get this Spurman's Majoranas is to rewrite it in this Majorana basis and to look for two operators that sort of drop out of the Hamiltonian. And then comes why the quantum dots. So the experimental motivation comes from the fact that the quantum dots have been studied for many, many years, and experimentalists have a very good control about the systems. So already there was experimental paper that demonstrated that by considering a nanowire with two gate-defined quantum dots in superconducting region, one indeed can realize this condition for Pullman's Majoranas by tuning the hopping amplitude to be equal to delta and sort of screening the interaction effects. So to answer the question is the very special thing about these systems is that apparently they're accessible experimentally and there is a very good control. And now there are experiments with two quantum dots and with three quantum dots demonstrating that it is, under this very stringent condition, it is possible to realize this Pullman's Majorana bound states. Yes? So they in experiments, they measure the differential conductance as a function of the applied voltage. And if you have a peak at zero energy, it means that you have a bound state at zero energy. Whether it's Majorana or not, well, I would say we don't know. Yes, please.
Just a quick question. So regarding this Pullman Majorana, so the delta is still a P-wave superconductor?
Yes.
So you still need
yes, like it just couples to neighboring sites and there is no spin. So in principle, one can start with a microscopic model with two quantum dots with spin. They apply very strong magnetic field and then there needs to be like opposite spins in a setup. Yes, please, another question.
But for two sites, you assume it's proximity induced, right? Or
so in the theoretical proposal, so it's so there are two quantum dots, and you have a superconductor in between, and you assume it's a cross-Andreev pairing between the two quantum dots. So this is all very nice, but the thing is that this condition is very stringent, that one has to tune T to delta. And there have been a lot of theoretical proposals complicating system a lot on how to tune this T to delta and how to relax this condition. But the main point is that this theory does not allow to have any electron-electron interaction in the setup, which is in principle not the case for the quantum dot systems. So what we propose in our work is to take this two-side Kitaev chain model of this quantum dot setup and to put it in a cavity and then use the photon-mediated interaction in order to tune the parameters of the system such that we can realize the Spurman's Majoranas with photons and to alleviate this condition of T being equal to delta and zero electron-electron interactions. So we start with this very, very simple Hamiltonian and we keep couple it to a single mode cavity, and for the coupling we just use a pious substitution that draws the hopping between two neighboring sites C1 and C2. So how to solve this Hamiltonian? So of course we can do exact diagonalization in this many-body electron-photon basis, but then it doesn't really tell us whether we have this isolated Majoranas or not. And alternatively, we can derive an effective Hamiltonian with the goal of demonstrating that we really get the isolated Majorana bound states. So sorry, this is a little bit technical slide, but I will go through it very, very quickly. So the goal of deriving this effective Hamiltonian is to keep, let's say, the diagonal transitions and to, in the high frequency limit, to sort of neglect or say the transitions between different photonic subbands. So to do so, we use a projectors method, and this allows us to derive the effective Hamiltonian, this H tilde of n, that is now written still in this fermionic basis, but now all the parameters of the system, such as the strength of the electron-electron interaction, on-site energy, and the hopping between two neighboring states, they become renormalized by photons. And renormalized in a sense that now these parameters, they depend on the cavity frequency, they depend on the strength of the light-matter interaction, but also they depend on the Fock subspace in which we are working, or in which subspace the cavity was prepared, whether it was ground state or first excited state, and so on. And then, since we have this effective model, and I will show you in the next slide that it agrees very well in a high frequency limit with the exact diagonalization, we can try to derive the conditions to have this. Yes, Dennis?
If you do Schrieffer-Wolff, you would have some small parameter, right? But now it's here, what is your small parameter? Is there...
So we have a large parameter. So we say that we're in a strong cavity frequency regime, that omega c is larger than any other energy scale in the system, but we don't impose any conditions on the strength of the light matter coupling G. So we don't do any expansion here.
Good.
Here there's like an additional assumption that a cavity does not interact with a superconductor that actually induces this delta, right?
Yes.
So it's as if it was like somewhere else, basically, not in the cavity.
Yeah.
Because otherwise delta should also depend on
So it's a very good question, and maybe we can discuss later, because whether we should couple the superconducting term to the cavity or not. So from some symmetry arguments, I can argue why for a two-side system we should not do it, but if I believe that if we take a system with 3 sides or 100 sides, we should couple it to cavity, but yeah, maybe we can keep it for later. Thank you. Okay, so now our goal is to use this effective theory to derive the condition for the isolated Majorana bound states, and we do exactly the same as we did in the absence of the cavity. So we impose the conditions to cancel all the effective interactions between these Majorana operators gamma, and also to cancel any sort of coupling between these two Majorana operators gamma 1 and gamma 4, which are at the edges of the system and that we want to drop out of the Hamiltonian. And we can do so by imposing the condition that says that this cavity mediated interactions, they should cancel the column interaction already present in our system, and then our new photon-assisted tunneling should cancel the superconducting pairing term in our setup. And then in practice, how does it work? So instead of tuning T and delta and putting U equal to 0, now we can put any values of our column repulsion term. We can put any values of T and delta, but then we have to tune the strength of the light matter couplings and the cavity frequency. And by tuning these two parameters, we can reach the so-called sweet spot. And then if we calculate this many-body electron-photon energy spectrum, we can find that by imposing these conditions on our parameter, we have this degeneracy between even and odd parity ground state energies. And this plot, it's supposed to demonstrate that we have a very good agreement between exact diagonalization in red and this effective Hamiltonian H in two different colors. And then, of course, the very important question is how can we measure it in experiment? So since we're already working with photons, the most natural thing is to look at the cavity transmission, or a theoretician to look at a photon propagator D, which is just an A-Dagger correlation function. And it turns out that we can calculate the density of state of this photonic propagator, which is plotted here as a function of the frequency and the tunneling between two neighboring dots. And it turns out that at the point where we have this ground state degeneracy between even and odd parity sectors, we have this discontinuity between the peaks. So when we work in the even parity subspace, our density of states looks like this. And in the odd parity subspace, we have these two different peaks coming from the energy levels. But once we hit the sweet spot condition, there is this discontinuity that in principle we believe can be measured in the experiment. But the very important point that this degeneracy only tells us that there is degeneracy between even and odd parity ground states, but it does not tell us whether the two Majoranas talk each other through the column-column interaction. So there is still work needed on how to probe this Majorana localization or Majorana non-locality. So this brings me to the conclusion. So in this talk, I discussed how one can realize Pullman's Majoranas with coupling to the photons, and how one can derive these degeneracy conditions using the effective theory. And then, of course, the very important open questions from the field of the Majorana bound states is how we can probe their non-locality, how we can scale up this model to many more quantum dots so that we can get the topological protections. And for theoreticians, the important question is how to develop new methods to solve this coupled electron-photon system such that we can use, for example, mean field decoupling, and then include the fluctuations in our model. And of course, the acknowledgements to my two collaborators, Marco Schiro from Collège de France in Paris and Alvaro Gomez-Leon, who's in Madrid, and to the funding agencies. And with this, I thank you for your attention.
Nice talk. Questions? John?
Yeah, thank you. This is very cool. I guess maybe, well, to your last point, so could you use this scheme also to couple cavity photons to Majorana qubits and do some sort of transduction? And also conversely, would you worry about photon fluctuations decohering your Majorana qubits?
Okay, to answer your first question, the problem that the Majoranas themselves, they don't couple to photons because they don't have a dipole moment. So here we always have few additional levels in our setup. But then, of course, there are multiple theoretical works that consider effective models for the Majorana qubits, and they demonstrated that it's possible to do not by 4 rotations as just purely for Majorana qubits, by supplement them. And but the coherence, I don't know, maybe there are works, but I've never worked on open quantum system. I cannot comment on that.
Thanks.
Thank you. Very interesting. I have a very naive question.
Yes.
If I had 2 coupled spin-1/2 systems, if the singlet and triplet were degenerate, would you call that a poor man's Majorana fermion, or is there something more?
I would say there is something more. So in principle now in the community, people say that there are 3 conditions to have poor man's Majoranas. The first one is this ground state degeneracy. The second one is they should be localized at 2 opposite ends of the system, or each of them should be localized on their quantum dot, and they should not talk to each other through this column term. And the third condition is more general, that one should have a large excitation, a superconducting gap in a setup to protect them from the external decoherence.
Okay. Yeah, go ahead.
The microphone is off.
Yeah. So you're solving the condition for n equals to 1. Like, does that sort of assume that when you measure, for example, transmission, like you're using very weak light, and then is that a reason why you're, maybe I'm...
Okay, so we have these conditions to get this gamma 1 and gamma 4 to drop out of the Hamiltonian, and one of them is that we should screen the column interactions. It turns out that if we start with a repulsive interaction, we need to prepare the cavity in excited state with one photon.
So
that's why we work with n equal to 1. So if you say that we have attractive interaction between the quantum dots, which is not very physical, then you can work with a cavity with n equal to 0. But then in principle you have you need a strong light matter coupling, so it doesn't mean that G is small, so here G is sort of the order of the cavity frequency.
So this is part of your protocol, like you start with the cavity in single photon box state and then you probe it.
Have you thought about, in addition to the cavity, dressing the model, adding an additional drive that can scatter to the cavity and out of the cavity to modify the parameters?
No.
So just to make sure I understand, so the reason you use this poor Majorana chain is because it's easier to solve, or is there some physical reason?
The motivation comes in general from this field of Majorana physics, that part of the community is moving to, especially experimental one, to engineering Majoranas not with quantum wires, but really with these quantum dots. And now there are lots of efforts on how to tune the parameters of these Pullman's Majoranas and how then to do the scaling to large chains with quantum dots.
So if you were to use like the full long Kitaev chain in the cavity, so would you see any qualitative differences?
Okay. In principle, so the Majoranas themselves, they don't couple to photons, so you will not change the Majorana states, but you will renormalize your gaps in the system. And very interesting things happen if you want to use now the cavity as a way to probe these Majoranas or to probe these topological superconductors, because one can see the presence of the zero energy states. Then if one theoretically assumes that the cavity is not homogeneous, you can probe the non-locality, and yeah, we have some work on progress on this subject.
Okay, any other questions? Then let's, sure.
So, how do you, maybe I missed this point, how do you make sure the edge modes in the gap, they're not modified by the cavity mode? They will be shifted, I suppose, but I guess that can perhaps, then how do we, if they're shifted, how do we even explain the many-body degeneracy?
Okay, so in this situation, so we have just two sides. So there is no bulk, there is no topological protection. So these modes, they are called Pullman's Majoranas because there is no topological protection. And they couple to photons, and these photons, they completely change them. So for example, if you have a look at this energy spectrum, so for example, this blue lines is in the absence of the cavity and the red ones in the presence of the cavity. So they really shifted a lot by coupling to photons.
Okay, thanks.
Okay, let's thank Olesia again. Very nice talk.